Okay, so imagine like a principle that seems so obvious. And it's almost like common sense, right?
Uh-huh.
But then it's also so deep and like profound that it sparked, these huge debates
Right.
and kind of reshaped like all of mathematics and logic, as we know it.
Absolutely.
And you, dear listener, as a philosopher, I mean, you're no stranger to these kinds of paradoxes.
Right. Right.
And today we're going to dive deep into one of these paradoxes, the axiom of choice.
Yeah, for a mind like yours, I think this is going to be really interesting because, this isn't just some like dry technical math thing.
Yeah.
The axiom of choice, or AC as it's often called, really gets into the nitty-gritty of like what exists in math,
Yeah.
and how powerful our reasoning can actually be.
Exactly. So our mission today, and we're mainly going to be pulling from the Stanford Encyclopedia of Philosophy's entry on this,
Mm.
is to, not just say what the AC says,
Mm.
but to really understand like its philosophical weight,
Yeah.
the debates that it sparked about, what are the foundations of math and how it's like surprisingly connected to logic itself.
Yeah.
So think of it as like we're going to take apart its different forms and like poke at the basic questions that it raises about like what does it even mean for a mathematical object to exist and
Right.
what counts as like a legit proof in the first place.
Yeah. So let's just start with the axiom itself. In its like most basic form, what's the axiom of choice actually saying?
Okay, so let's unpack this. The axiom of choice basically says that if you have any collection of sets, like it doesn't matter how big or how complex they are,
Right.
as long as each set in that collection has at least one thing in it, it's non-empty.
Okay.
And as long as they don't share any elements, so they're mutually disjoint,
Hmm.
then it's possible to make a new set by taking just one thing from each of those original sets.
Gotcha.
And this new set, it's often called a transversal or a choice set. And that initial reaction that you might have, that this is just like totally obvious, right?
Right.
That's actually really common. The encyclopedia points this out,
Uh-huh.
that it feels like something we should just be able to do, intuitively.
Yeah, totally. It's like if you have a bunch of bags and each one's got, at least one thing in it.
Right.
The axiom's like, yeah, you can reach in, take one thing from each bag,
Right.
and now you got a new collection. Like,
Yeah.
seems pretty simple, right?
It does, right? But then the encyclopedia, they quote Frankel, Bar Hillel, and Levy, and they call it probably the most interesting axiom of mathematics, second only to Euclid's axiom of parallels.
Oh, okay.
So like that kind of statement, it makes you wonder what all the fuss is about, right?
Yeah, for sure.
Yeah.
That really emphasizes how deep this axiom goes.
Right.
And while it might feel, correct on the surface, it has these huge consequences in math, a lot of which we couldn't even do math without.
Right.
And some of them are pretty mind-blowing. And it's become like a major topic in the discussions around, the foundations of mathematics. So yeah, this axiom, or, different ways to say it, is a real workhorse in a lot of areas of math these days.
Yeah, and here's where it gets really, really interesting for us as philosophers.
Okay.
So the story of the axiom of choice really takes off with Ernst Zermelo back in 1904.
Okay.
He first laid it out using this idea of coverings. So he thought, like, imagine that for every non-empty subset of a set, you could somehow pick out a single element from it.
Right.
And he called it distinguish. Like, it was special,
Yeah.
And his initial way of saying it basically claimed that, like, this picking process,
Uh-huh.
it's always possible for all the non-empty subsets of any non-empty set.
Okay, so this idea of a distinguished element, this choosing thing,
Right.
that morphed into the more formal idea of a choice function, right?
Exactly, yeah. A choice function for a given collection of sets that are non-empty, it's just like a rule
Right.
or a map that just picks out one thing from each of those sets.
Right.
So the encyclopedia gives this basic example using the non-empty subsets of a set, just 0 and 1,
Okay.
which are, the set of 0, the set of 1, and then the set with both 0 and 1.
Okay.
And they point out that there are actually two different choice functions you could define for this, like tiny little collection.
So even in this like really simple finite example,
Right.
there are multiple ways to make those choices.
Yeah.
And, from a philosophical point of view, that's kind of interesting.
It is, yeah.
And the axiom's power and where the philosophical debate really starts
Yeah.
is that it says at least one of these choice functions has to exist even for collections that have like infinitely many sets.
Exactly. Yeah, and so Zermelo's first formulation of this, it's often labeled as AC1,
Right.
which says that like any collection of these non-empty sets has a choice function it can actually be said in a bunch of different ways, and each one gives us like a slightly different perspective on this whole idea of choice, you know?
Okay.
So one important way of saying it again is in terms of indexed sets, which is AC2,
Right.
which says that any indexed collection of sets also has a choice function.
Okay.
And the encyclopedia kind of informally says it as like uh, a variable set with an element at each stage has a variable element.
Oh, that's a very intuitive way to put it, especially if you think about collections that might be indexed by, something way more abstract than just the
Yeah.
natural numbers.
Yeah.
It really highlights that idea of picking at each stage of maybe an infinite process.
Right, exactly. And then we have AC3, which talks about relations between sets.
Okay.
So it says that if you have any relation, let's call it R, between a set A and a set B,
Right.
such that for every element X in A, there's at least one element Y in B that's like connected to it by R, right?
Okay.
Then there's got to be a function, call it F,
Mhm.
from A to B, that basically chooses one of those related YS for every X in A, meaning R of X and F of X is true for all X in A.
Gotcha.
So to put it simply, every relation that covers its entire domain has got to have a function with that same domain.
Okay. So that takes us to AC4, which says that any surjective function, which is a function where everything in the codomain is mapped to by at least one thing in the domain,
Right.
has a right inverse.
Yeah.
And this right inverse basically chooses one of the elements of the domain that maps to each thing in the codomain.
Right.
So all these different formulations, they look different on the surface,
Yeah.
but they all get at this core idea of selection.
Right.
And they're all amazingly equivalent in standard set theories.
Yeah.
It's like this fundamental concept of choice
Yeah.
has all these different faces in math.
Yeah, it's kind of cool. So in 1908, Zermelo actually gave us another way to think about AC, and it's called a combinatorial formulation called CAC.
Okay.
And this uses the idea of a transversal or a choice set for a family of, mutually disjoint non-empty sets.
Right.
So remember, a transversal, it's just a subset that intersects each set in the family at exactly one element, right?
Yeah.
So the encyclopedia gives this clear example. Like if we have a family of sets and it's just the set of 0, the set of 1, and the set of 2 and 3,
Okay.
then sets like 0, 1, 2, OR 0, 1, 3, those are transversals.
Okay.
And Zermelo argued that this formulation, it had like a purely objective character,
Yeah.
and it seemed to kind of sidestep this idea of, actively making choices, which was like the contentious part.
Right.
He even offered this like combinatorial justification where he said you could take a selector that hits every set and then
Okay.
kind of thin it out to just have one element in each.
Okay.
And which is interesting because the encyclopedia points out that this hints at a connection to Zorn's lemma,
Oh, yeah.
which is this powerful principle about ordered sets that we'll get to later. But Zermelo, he was really careful to emphasize that for finite collections, both AC1 and CAC, you can actually prove them using just the basic ideas of set theory that pretty much everyone agreed on.
Okay.
The real philosophical problem, like the thing that everyone was arguing about,
Yeah.
is when you start talking about infinite collections, even if each set in those collections is finite,
Right.
and the example that they give in the text, like pairs of real numbers versus pairs of arbitrary sets of real numbers, that really shows this jump in complexity when you're dealing with infinity.
Yeah, that makes sense. So if it seemed so, straightforward for finite sets, why did Zermelo even bother introducing this axiom for infinite sets in the first place? It seemed kind of problematic to some people.
Yeah, so his main motivation, and this is crucial for understanding the philosophy behind it, was to give a solid foundation for one of the cornerstones of Cantor's work on set theory, the well-ordering theorem.
Okay.
So this theorem, it says that any set, no matter how big or strange it is, can be ordered in a way that every non-empty subset of that set has a least element.
Right.
So according to that ordering, so there's always a smallest thing in every subset.
Okay.
And this is where the philosophical fireworks really start.
Oh, okay.
So in 1904, when Zermelo introduced the axiom of choice and then used it to prove the well-ordering theorem, he got a lot of criticism.
Oh, wow.
And the main objection, especially from mathematicians who are into this constructive way of thinking about math,
Mm-hmm.
like Baer, Borel, and Lebesgue, they all focused on this highly non-constructive, even idealist character of the axiom.
Interesting.
So their argument, which came from their philosophical view of math, was that the axiom just claims that you can make maybe even uncountably many random choices
Right.
without actually giving you any concrete method or algorithm to define how you'd actually make those choices.
Oh,
So this really gets to the heart of this big philosophical divide in math, this question of like, what does it even mean for a mathematical object to exist, right?
yeah, yeah.
So for these constructivist mathematicians, an object only existed if you could describe it uniquely or like build it constructively.
Right.
But the axiom of choice seemed to bypass this.
Yeah.
It said things existed just because it was possible, but it didn't give you the recipe to make them.
Yeah, it's like saying, like, there's a cake, but not telling you how to bake it, you know?
Exactly, yeah. Like it's out there, but good luck finding it.
Yeah, exactly.
So Zermelo, he wasn't just going to ignore these criticisms. So in 1908, he responded,
Uh-huh.
and he tried to address these constructivist concerns in two ways.
Okay.
So first, he restated AC in terms of those transversals that we talked about, hoping that this combinatorial perspective would feel more concrete
Right.
and less about these abstract choices.
Yeah.
And second, and this is maybe even more important for how math developed, he actually laid out all the other axioms of set theory that he needed to prove the well-ordering theorem.
Okay.
And that was basically the birth of modern axiomatic set theory as we know it today.
Wow.
So as this like foundational debate was going on, something really interesting happened. Mathematicians started realizing that they were actually using the axiom of choice, like all over the place, often without even realizing it, to prove these important theorems that had been accepted for a long time.
Okay.
So this made a lot of prominent mathematicians like Hilbert start to see it as like not some shady assumption,
Right.
but as a fundamental principle of math that they needed for a lot of their reasoning.
All right.
Hilbert even thought that his epsilon operators, which is this way to pick out an object that fits a certain property, were like choice functions at their core.
Interesting. So even with it being so useful and accepted more and more, the philosophical worries about AC, they didn't totally go away, right?
Yeah. No, they didn't. And those lingering doubts, they were often, fueled by these like really bizarre and counterintuitive consequences that seemed to come from assuming AC was true.
Okay.
And the most famous one, the one that really messed with people, is the Banach-Tarski paradox.
Oh, yeah, the Bennett-Tarski paradox. That's the one that sounds more like a magic trick than math, right?
Yeah, exactly. It's like, poof, two spheres.
Yeah.
So the encyclopedia kind of touches on it,
Uh-huh.
but it basically says that if you assume the axiom of choice is true, you can take a solid sphere in 3 dimensions, cut it up into a finite number of pieces, and then rearrange those pieces without stretching or distorting them at all.
Right.
And you can make 2 spheres that are exactly the same size and shape as the original one.
Wow.
Yeah, and you could even theoretically make a sphere of any size you wanted.
Wow.
It really messes with your like basic understanding of how physical reality should work.
Yeah, totally. It's seriously counterintuitive.
Yeah. It is. It's like it makes you question like if that's possible, what else is?
Right.
So no wonder it made some mathematicians and philosophers really uncomfortable about like the basic principles of math.
Right. It seems like you could, get something from nothing in terms of like volume and quantity.
Yeah, it does. It's like something straight out of a sci-fi book.
Totally. So this paradoxical result, understandably,
Mhm.
made some mathematicians question like the very foundation of how this could even be derived.
Right? It's like, hold on, if this is true, what else have we been wrong about?
Yeah, exactly. It challenges our like geometric intuition at a very fundamental level.
It does. And it wasn't until the mid-1930s that the whole issue of AC's place in math was kind of cleared up,
Okay.
thanks to Kurt Gödel.
Oh, Gödel.
And his groundbreaking proof that AC is relatively consistent with the other standard axioms of set theory.
Okay, so Gödel showed that if the standard axioms of set theory, like the axiom of union or the power set axiom, all those, if they're all logically consistent, like they don't lead to contradictions,
Right.
then adding the axiom of choice to that system doesn't mess things up.
Okay.
It doesn't introduce any new contradictions. So it's safe in that sense.
Okay, so he's saying it's like compatible with what we already accept.
Yeah, exactly.
But how did he like actually prove this?
So Gödel's proof,
Mm-hmm.
it was really deep and technical.
Okay.
It relied on this complex idea of definability and making this specific model of set theory called the constructible universe, which is usually shown by the letter L.
Okay.
So he built up this hierarchy of sets called L alpha inside this bigger, more inclusive hierarchy of all L sets, which is V alpha.
Okay.
And the main idea is that at each step in building L, you only include the subsets that you can define in a precise way using the sets that were already made in the previous steps.
So it's like a more restrictive way of building the universe of sets?
Yeah, exactly. Think of
Oh.
it like Gödel made a more careful or restricted universe of sets, where you can only have sets that have a clear and definable origin.
Okay, so he's like filtering out the weird ones.
Yeah, kind of. So he basically showed that if we just stick to this more constructible universe of sets, then the axiom of choice holds true in that universe.
Okay, so in his universe, it works.
Yeah. And what's cool is Gödel showed that in this L universe, all those standard axioms of Zermelo-Fraenkel set theory, they all hold true.
Okay.
And importantly, the axiom of choice holds true too.
Okay.
So that means AC is relatively consistent. It works with the rest of set theory if we assume that set theory itself is consistent.
Right, okay. So the encyclopedia also mentions that there's a simpler proof for the consistency of AC using something called ordinal definability, and the classes OD and HOD.
Yeah, so the basic idea there is to look at sets where all the elements and the elements of their elements and so on can all be defined using ordinal numbers.
Okay.
And those are basically like the counting numbers, but extended forever.
Right. Okay.
And the class HOD, which stands for hereditarily ordinal definable sets, makes up another model of set theory.
Okay.
And in that model, it turns out that the axiom of choice also holds true.
Okay.
So, again, this proves that AC is consistent with those basic set theory principles by showing that there are, well-behaved universes of sets where AC is true.
So Gödel showed that AC is like safe to use, meaning
Yeah.
it doesn't break set theory if we assume set theory is already consistent.
Right.
But what about the other side of the coin?
Uh-huh.
Like, could we actually prove the axiom of choice from the other axioms of set theory?
Yeah.
Like, is it a necessary consequence of how we understand sets?
That's a great question. And that's where Paul Cohen's work in 1963 comes in.
Okay.
He used this groundbreaking technique called forcing
Okay.
to prove that the axiom of choice is actually independent from the standard axioms of Zermelo-Fraenkel set theory.
Okay. So that means that you can have models of set theory where all the standard axioms work. But the axiom of choice is, like, demonstrably false in those models.
Exactly. And that was a huge revelation about the nature of this axiom.
So independence, it means that, like, AC is neither a logical necessity
Right.
nor a logical contradiction.
Right.
It's like this separate assumption that we can either choose to include or not, and that choice will lead to, like, different mathematical universes.
Exactly. And that's a big shift in perspective from how people saw it before.
It is.
Cohen's method of forcing, it was a game changer in set theory.
Okay.
It gave us a really powerful tool to show the independence of lots of set theoretic axioms.
Right.
But even his proof, as the encyclopedia points out, it built on earlier ideas about permutations and symmetry.
Okay.
Kind of like how Abraham Frankel showed the independence of AC from a set theory that included atoms.
Yeah. Those atoms being, like, pure individuals, they don't have any members themselves.
Right.
Unlike the empty set, which is a set with no members.
Exactly. Frankel's big insight was that if you've got a bunch of these atoms that are totally indistinguishable,
Okay.
then any operation that just switches them around,
Yeah.
what we call a permutation, should keep the overall structure of that mathematical universe the same.
Okay.
So he was able to build a specific symmetric model of set theory that had these atoms, where you could
Huh.
show that a collection of pairs of atoms didn't have a choice function.
Okay.
And that was an early sign that AC wasn't just a consequence of other basic set theory principles.
So basically, Gödel and Cohen's work together tell us that the axiom of choice is neither provable nor disprovable from the standard axioms of set theory.
Right.
It's independent, like it stands alone.
Yeah.
So this leads us to think about how it relates to other big ideas and theorems in math.
Absolutely. So the axiom of choice is really tied up with a whole bunch of propositions called maximal principles.
Okay.
And these principles generally say that if you have a partially ordered set, which is just a set where some things might be operable, some things might not.
Okay.
Under certain conditions, that set has to have at least one maximal element, which is just an element that's not strictly less than anything else in the set according to that ordering.
So it's like the top dog, right?
Yeah, exactly.
But how does this idea of maximal elements in these, like, ordered sets connect to, like, the simple act of choosing stuff from a collection of sets?
So think back to AC2, the one that says any index collection of non-empty sets has a choice function.
Okay.
Now imagine you're trying to actually build one of these choice functions.
Okay.
So we can look at the set of all partial choice functions, which are functions that have only chosen an element from some of the index sets, not all of them.
Okay.
And we can order these partial choice functions based on whether one extends another, meaning it's chosen from more sets.
Okay.
So a maximal element in this set of partial choice functions would be one where you can't choose from any more sets while still being a choice function. And that maximal partial choice function would actually be a choice function for the whole original collection of sets.
Okay.
So if there's a maximal element in this ordered set of partial choices, it means there's a full choice function.
I see the connection there.
Yeah.
So, and the most famous of these maximal principles is Zorn's lemma, right?
Right, exactly. Zorn's lemma says that if you have a non-empty, partially ordered set,
Mm-hmm.
and every chain in that set, which is a subset where everything's comparable,
Okay.
has an upper bound in the set, then that set has to have at least one maximal element.
Okay.
And a set like that is called an inductive, partially ordered set.
Okay.
Zorn's lemma always seems kind of intuitive to me, even though it sounds kind of abstract.
It does, yeah. And the encyclopedia even gives this informal argument, right?
Yeah, so it's like you keep picking bigger and bigger elements in this set.
Right.
And if you never hit a maximal element, the chain you build has to have an upper bound in this set.
Right.
Then you can keep going.
Mm.
And it seems like you have to eventually get stuck at a maximal element.
It feels like you should, yeah.
Yeah. That informal reasoning gets at the basic idea. And the really important thing for us is that you can actually prove Zorn's lemma from the axiom of choice using standard Zermelo-Fraenkel set theory.
Oh, okay.
And in that proof, the axiom of choice lets you choose the next element in the chain when you haven't found a maximal element yet.
Okay. The encyclopedia mentions some equivalent ways to say Zorn's lemma
Yeah.
using things like nests and strongly inductive or strongly reductive families of sets.
Yeah, those are just different ways of saying the same thing, really.
Okay.
So a nest is just a bunch of sets where for any two sets, one is always a subset of the other.
Right.
And a collection of sets is strongly inductive if the union of any nest in it is also part of that collection.
Okay.
So you can say Zorn's lemma as any non-empty, strongly inductive collection of sets has a maximal member.
Okay.
And then there's the opposite, strongly reductive families, which means they're closed under intersections of nests,
Uh-huh.
and that guarantees a minimal element.
Okay, so it's like flipping the script.
Yeah, exactly. And the cool thing is you can actually derive the axiom of choice, especially AC2, the one about index sets, pretty easily from Zorn's lemma in its set theoretic form.
Oh, okay.
So as we talked about before, the set of all partial choice functions is a non-empty, strongly inductive collection.
All right.
And Zorn's lemma guarantees that there's a maximal element in that collection, and that's the choice function we're looking for.
Gotcha.
And similarly, the combinatorial axiom of choice, CACI, you can also derive that from Zorn's lemma.
Okay.
The encyclopedia outlines how to do this by looking at samplings of the mutually disjoint sets.
Right.
And those minimalist samplings, they turn out to be the transversals, or choice sets we're interested in.
Okay.
And the collection of all samplings is strongly reductive. So there has to be a minimal sampling, which is a transversal.
So Zorn's lemma and the axiom of choice are logically equivalent in standard set theory.
Exactly.
They're like two sides of the same coin. Yeah.
And the encyclopedia points out that proving Zorn's lemma from AC is actually more complicated than the other way around.
Yeah, that's right.
But this equivalence, it really shows how important this idea of choice is
Yeah.
in the foundations of mathematics.
It really does. It shows that being able to pick things from collections of sets
Right.
is really closely tied to the existence of maximal elements in ordered structures.
Yeah.
It's a fundamental principle that shows up in different ways.
Right. And beyond these connections to other axioms and principles, the axiom of choice is used in a crazy amount of applications all over math.
Absolutely, yeah.
Like, it's used to prove so many crucial theorems.
And some of those applications are so basic, they're actually logically equivalent to the axiom of choice itself.
Okay.
So as we talked about, the well-ordering theorem, which is what Zermelo wanted to prove with AC in the first place, is the best example of this.
Right.
In standard set theory, those two statements are inseparable.
And another early one that's equivalent is Bertrand Russell's multiplicative axiom.
Okay.
It says that if you take the Cartesian product of any collection of non-empty sets, the result is also non-empty.
Right.
And that
Yeah.
makes sense because if each set in a collection has at least one thing in it,
Yeah.
then their Cartesian product, which is all the possible combinations you can make by taking one thing from each set, will also have at least one thing in it,
Right.
meaning it's also non-empty. So you can make those combinations, which is basically like making a choice from each set.
Yeah, okay, that tracks. So the encyclopedia lists a bunch of other early applications of the axiom of choice,
Right.
and it carefully notes whether each one is weaker than, equivalent to, or just a consequence of some other principle.
Uh-huh.
So, for example, the idea that every infinite set has to have a countably infinite subset,
Right.
that's actually weaker than the full axiom of choice.
Okay.
But you can't prove it without some kind of choice principle.
Interesting.
And then there's this, like, maybe less intuitive statement that every infinite cardinal number is equal.